Hi there. Let's continue solving our question for EndSem paper. This is question number 6, part A, which is to describe how the coefficients in linear regressions are estimated either using the closed form equation or the gradient descent. So let's start. Uh, for the linear regression coefficient estimation, we know that linear regression seeks to model the relationship between information and continuous output variables. Conceptually, it assumes that the target value can be expressed as the weighted sum of the features plus an intercept term and some irreducible error. So formally, the model assumes that y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus and so on till beta n xn and some irreducible error eta. So b naught is the intercept. This is the inherent bias. Bi, any beta, represents the influence or weight of each feature. Eta represents the random error not captured by the model. To simplify relation, the formulation can be written as a matrix that y is equals to x beta plus eta. So x is the design matrix containing all the list of features, and beta would be the vector of coefficients we want to estimate. However, we can simply write this out as the linear combination. So the objective of model training here is to determine the coefficient vector that minimizes the error between predicted and actual outputs. The most common measure of error is the sum of squared residuals, so which forms the basis of the ordinary least square method. And the closed form solution to this, the normal equation, provides an analytical solution by minimizing the squared residuals. We take the derivative of cost function with respect to the coefficients and set it to 0 and solve for beta. So this gives us the normal equation. Beta cap, that is any beta, is given by the transpose of x matrix into the x matrix itself. The entire thing's inverse is multiplied with the x matrix transpose, and then it is multiplied into the y, that is the function, that is the predicted value for beta that is being processed. This formulation directly computes the optimal coefficients through matrix operations. It has several notable properties, such as it provides only one exact solution, not an approximation. There is no iterations or anything. It is a straight solution. It is most efficient for small to medium sized data sets. Primarily drawbacks is the computation cost, like calculating the x transpose into x, the entire things inverse scales on the order of like I believe the order of NQ. So it is very impractical when the number of features is very large. Despite this limitation, the closed form approach remains an attractive and interpretable modeling for small data sets. But the gradient descent method is usually used for real databases. When databases grow in size, especially in high dimensionality settings, computation of inverse of this inverse of x transpose into x is prohibitive. So we use gradient descent optimization, where we in each iteration we are performing the update rule. So gradient descent iteratively updates the coefficient vector using the direction of steepest decrease in the cost function. So the update rule is that beta is truncated by beta minus alpha into the derivative of the cost function with respect to beta, where the uh, j beta is basically the cost function, usually the mean squared error, and alpha is the learning rate controlling how large each update is. So there are several like variants of gradient descent. Number one is batch gradient descent, which computes the each which basically uses the entire data set to compute each update. Actually it is slow but accurate for large data sets. Then we have stochastic gradient descent, which uses a single data points per update, much faster and scalable, but very noisy and very unstable. However, stochastic gradient descent does not get stuck in the local minimas. and thus gradient descent is especially powerful to train our linear regression models because it is effective for very large data sets. It integrates naturally with regularization methods such as ridge and lasso. It provides the extension to complex models beyond linear regression. So we also know that regression and its impacts are like the when the data set has many features, has exhibited multi-collinearity, the plain OLS solution can become unstable. Regularization basically introduces a penalty term to mitigate this. We have ridge regression and lasso regression, where ridge regression uses L2 penalty, which modifies the closed form solution by adding this lambda I to xt and x. And for L1 penalty, for L2 penalty, we are just subtracting the value of summation of all the betas uh, squared. And for L1 penalty, we are basically subtracting the absolute value of the summation of betas. Both provide a unified framework for incorporating penalties, further reinforcing its value in modern machine learning workloads. So let's move on to the second part of the question. Explain logistic regression and use the logistic regression to calculate the probability of a class for a given input example. Let's move on to that. So logistic regression is a statistic method used for binary classification problems. When output variable has two possible classes such as pass or fail, yes or no, or 1 or 0. So, unlike linear regression, which predicts continuous values, logistic regression predicts the probabilities that a given input belongs to a particular class. So, to achieve this, we first compute the linear combination of the input features, that is, z is given by the beta naught plus beta x1 plus beta 2x2, and so on and so forth till the nth beta xn and beta n and xn. However, this linear output can take a real value, so it can be transformed into probability between 0 and 1 using logistic sigmoid function. So the logistic sigmoid function is given by 1 upon 1 plus e to the power of minus z. This function ensures that the model's output uh, represents a valid probability belonging to the positive class. So an example here that we have is the predict whether the student passes an exam based on their study hours. So we first estimate the beta naught and beta 1 at minus 4.5 and 1.2 for students who have studied 5 hours. So x is equals to 5. We first calculate the compute the linear combination. So the linear combination would be minus 4.5 into 1 plus 1.2 into 5. So that would give us 1.5, and then we need to apply the sigmoid function to calculate the probability. So that would be given by the expression of p of y equal to 1 and x equal to 5. So 1 upon 1 plus e to the power of minus z. So minus z is given as 1.5, and thus we calculate the probability as 0.818. That is, the model predicts that 81.8% with 81.8% probability that the student shall pass, and otherwise the if the probability of any given output is greater than zero point 0.5, then the class predicts class 1, that is pass. That means the student shall pass. However, in the other case, when the value is less than zero point 0.5, the model predicts class 0, that is fail. This threshold can be adjusted depending upon the application and can be determined by advanced techniques such as the area under the curve of an ROC, receiver object correlation plot, which can help us determine a better machine learning model. So that would be it. In the next video, we shall solve the question number 7. Thank you.